That's good. Oh, okay.
He's my requirement, but I sort of told him I'm heading to class.
David?
Nooner. He said he knows you. He didn't know if you knew him.
From where?
He's the choir director at Specification.
Oh, okay. All right. I'm not really good with names.
No, I don't.
All right. C. Okay, that's good. Alrighty. Are you guys ready? Are you ready for the weekend?
Yes.
Okay, very good. So we are continuing with this. I'm going to cough a little bit today, but I am going to try my best not to cough too much. I just took 2 of these mucus relief pills. And I have a whole big bag of not food, but medication ready. So I'm ready to suppress my cough as much as I can. So hopefully we can get through all of this stuff here. So last time we talked about bijective function. Yes?
Is it recording?
I believe so. Yep, it is recording. Very good. But good to check. Always good. Okay. So last time we talked about bijective function. This is where we left off on Tuesday. So a bijective function is really simple because it's just a function that is both injective and surjective. That's it. That's all it takes for a function to become bijective. But the importance of being bijective is really far-reaching because a bijective function is actually 2 functions in one, because it can go in one direction, but it's also a function going in the opposite direction. It is guaranteed. Okay, and I also explained how bijective functions are very useful for debugging programs because it allows you to execute a program backwards. Okay, if you know what is the state of a variable after it is getting updated by a bijective function, you can always reverse it back to the value of the same variable before it got updated. Okay, so how do you guys still remember that much? Okay, very good. All right, so one way to define the inverse function is basically to say if for everything that is in F, okay, if you find xy as a 2 tuple in F, for each one of those, yx, which is basically the same 2 things in the 2 tuple but in a reverse order, as a 2 tuple, that has to be a part of F inversed. Okay, so that's basically the inverse function. Now there's a little bit more because you cannot have any more than these as well. So they should have exactly the same number of elements. F versus the inverse of F, they have the same number of elements. All right. Are there any questions about this slide or anything prior to this? Any other questions about injective or injectiveness or surjectiveness? Because this would be a good time to talk about those things before we move on. Any questions? Questions? All right. So we'll talk about the composition of functions. A composition of function, I'm pretty sure you learned about this in math classes already, is when you have a composite of two functions. You apply the result of function as a parameter, so to speak, or as an argument to another function. So in this case, I have an example where f of x is defined to be 3x plus 5. The x is really arbitrary. Okay, remember this x here is just denoting a variable so that I can express how f is defined by basically saying, okay, whatever is in the parentheses, multiply that by 3 and then add 5 to the whole thing, to the product. That will be the value of f. So I can use, I can define g of x to be 3x, okay, just randomly define these things. But the key now is this reversible? In other words, is this a bijective function? So when I ask you whether it's a bijective function or not, the first thing you should think is, okay, is it injective? And also, is it surjective? Is this injective? What does it mean to be injective?
Every x value is mapped.
Sorry?
Every x value is mapped. Every x value is mapped.
Every x value is mapped.
With different.
That would be just a function. Yep.
Every x value is mapped to a different.
Unique. Yep. So every x value maps to a unique value in the domain. So can you say that is true for 3x plus 5 as a function?
Yes.
Yep. Okay. If x is different, 3x plus 5 is going to be different. Okay. Very good. What about 3x? Function g. Same thing. They're both injective. What about surjectiveness? And in this case, let's just deal with. We can deal with real numbers. Okay. So just think of real numbers. In real numbers, is 3x plus 5 surjective? If I give you a value and I say, oh, this is the result of 3x plus 5, can you find x for that particular value?
Yeah. Yes.
That makes it surjective, okay? Because everything in the domain is mapped from everything in the codomain is mapped from the domain, okay? Can you say the same thing about 3x? If I give you a particular value, remember this one's going to be a little tricky. If I say this is the result of 3x, can you find the x for me? Okay? Yeah. So they're both injective and surjective at the same time, which means both of these functions are bijective. Okay, very good. Now that is actually an important thing. So if I want to define, I guess I used the wrong. Nope, this is fine. So I want to define a. It can be broken. Okay, so it's breaking this into two functions. So here's h of x, which is just adding 5, x plus 5. So f can now be seen as a composite, which is taking the result of g first and then apply h to it. Is that making any sense? Because g of x is 3x. So what do you do about 3x when you apply h to it? You're just adding 5 to it. So when you have h applied to g of x, then you have the same thing as the original f of x. Are there any questions about this part? Okay. So the notation, I actually got this corrected last semester because I was doing it in the opposite order. So I think I'm just going to check with you guys again. Is this the correct order? You apply h last. Okay, so g is done first, and then you apply h as the last one. Okay. Now, because h is reversible, has an inverse, and g has an inverse, f also has an inverse. So the composite, if the composite has components and all the components are have inverses, then the composite itself also has an inverse. So in this case, the inverse is basically the inverse of g applied to the inverse of h. So the inverse of h is applied first to the variable, and then you apply the g inverse to it. Well, let's see whether it makes sense or not. Okay, so let's work this out. Because I want to prove this, right? So how do we prove that is actually true? Okay, so I'm gonna use my MathJax previewer because I got it done for a reason. I need to use it. Okay, so we start with the definition of. Okay, so we need to make sure that we start with these notations. So we start off with g of x being 3x. Right? So if that is the case, what is the inverse? Yep, go ahead.
G equals 1/3 x.
The inverse, if going in one direction you're multiplying by 3, then going the opposite way you're just dividing by 3.
Yeah.
Okay, very good. So we'll go ahead and denote that. It's a fraction of x3. There we go. Is that okay?
Yeah.
All right, cool. So now we can also say, okay, what about h? h of x is defined to be x plus 5. Okay, that's just coming from the notes. What about the inverse of that? So h inverse of x. How do you reverse the operation of adding 5? Subtract 5. Okay, so x minus 5. There we go. Very good. So I claim that f, okay, is defined to be, so f is the composite of those two. I'm gonna have to cheat here because I forgot how to make that circle thingy. So if I forget, just right click, look at the tech command. Okay, CIRC is the command to do it. Okay, there we go. Switch back to the other side. Whoops. Too many tabs. Or did I open a new window? No. It's next to it. There we go. I'll put this into its own window because this way I can use Alt Tab to switch between the two screens. Okay, so f is known to be h with a little circle g, right? And it is, so f of x is going to be what? 3x plus 5. Okay, very good. 3x plus 5. Okay, so far it's just being copying stuff from the notes. So now I claim that f inverse, okay, so f, the inverse function of f is the inverse function of g inverse circle h inverse. There we go. Okay, so this is what I'm claiming. So if we look at f inverse of x, what does it look like? Well, I have the individual individual functions already defined. The inverse function of g is x divided by 3. The inverse function of h of x is x minus 5. So in this case, we are applying h inverse first. So that means we are doing the subtract by 5 first. Okay, so we say, okay, we are subtracting x by 5. And then what do we do?
Divide by 3.
Divide the whole thing by 3. Okay, so one way to do this is to put a fraction here. Put a 3 here. So the question is that really the inverse function of 3x plus 5? Looks that way. I mean, intuitively it seems like that is the case. But can we prove it? How do you prove that something is the inverse function of something else? Using algebra.
Swap the, well, you substitute that you substitute you substitute f into f inverse and it returns into something that returns to x.
We try to look into this, right?
Yeah, you simplify.
And also the other way around. Okay, so we look at, okay, if I apply f inverse first to x and then we apply f to that thing, do I get back to just x? And we can also do it the other way around. Okay, so we'll double check. We'll check this one first. Let's figure out what this is going to do. Okay, so what is this? Well, let's do it like this. Okay, so we know what is f inverse. So f inverse is this here. I'm just going to be lazy and just copy and paste it. Is that making any sense? You guys just have to focus on the top where it is already rendered. Is that making any sense? Okay. So now we want to take that and say, okay, now we want to apply f. So we want to multiply this whole thing by 3 and then plus 5 to it. So let's go ahead and do that. I'm just trying to figure out what is the best way to do this. So I'm going to go do a 3 something plus 5 and then just copy and paste the whole thing. I think the result is fairly clear even without doing this, but I just want to show it here. The 3 and the 3 cancel out, right? So we end up with just x minus 5, but then we add 5 to it. So we end up with just x. Oops. Oh, because that's outside of the entire area, so I have to do it here. So that's a proof that f and f inverse. One is definitely the other one's inverse. Is that okay so far? Okay. And that's it. That's the whole idea of composition of functions. All right. Are there any questions about functions up to this point? Nothing. All right. I'm not sure whether I really want to get into this at this point, but I'm going to try it. Okay. Because this is actually going to be a recurring thing that we'll see at least a few times in this class. It really is just the result of sorting. I want to express what does it mean to have an array sorted. I give you an array, you give me back after you sort it. How do I know, how do I qualify that it is actually sorted? How can I use mathematical symbols, mathematical language to express and say that, okay, this is the original stack of cards or the original array, this is the array that you give back to me, and the one that you gave back to me is in fact the sorted version of the one that I gave you. Okay, that's the question. Seems pretty easy, right? Everything should be in order. So let's go ahead and go through a few iterations of how we can express that. And I'm going to do it this way before we get into the actual way of doing it. So how do you express an array is sorted by a sorting algorithm? So let's go ahead and give it a few tries. So let's say assume the array in question has a name of A. Okay, just for simplicity. So if you want to say the array is sorted, it's pretty easy because all you have to do is to say A bracket 0, and let's say it is in a non-decreasing order. So it's less than or equal to A bracket 1, which is less than or equal to A bracket 2, and so on, all the way up to A bracket. And I'm going to use bar A bar to mean the quote-unquote cardinality, but this is not cardinality, this is the size of an array. This is the number of elements in an array. But the last one has an index of the number of elements in an array minus 1, so we have to do this. So if this condition is true, if A bracket 0 is less than or equal to A bracket 1, and a bracket 1 is less than or equal to a bracket 2, and so on, blah, 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 all the way up to the last element, then this array is in fact sorted. Okay? But the question is it the sorted version of the array that I gave you? Okay? Because to make an array meet this requirement is easy. I'll give you an example. Okay. So let's say, sort an array. Okay, this is actual, C code, or I try my best to make this a C code. Okay, so this is a, passed in as a pointer, because this is how you pass an array into a subroutine. And you also need to tell me how many elements are in the array, because in C and C++, the size or the number of elements of an array does not go with the array itself, so you have to pass that as a separate parameter. All right, so I want to write a sorting algorithm. If the only thing I need to do is to make the array meet this requirement, it's easy, okay? Because I can do something like this. For int I equals to 0, I is less than n plus plus I, a bracket I is that. But is this sorting? No, it's not sorting, but it makes the array meet that very simple requirement. What is it telling you? Exactly, we're missing something in the description. Okay, it's kind of like, when you tell a child what to do, when your description of what needs to be done or what the criteria is not clear, then something bad or something unintended can happen. For instance, give you a very good example. If you tell a child and say, I don't want to see any dirty dishes in the kitchen, okay? And your intention is, I want you to collect all the dirty dishes and wash them and put it back into the cabinet. But to meet the requirement of not seeing dirty dishes or not being found, it's easy. Just throw all of them away. Right? You go to your dumpster and you go to your trash can and go like, hey, how come all the dishes are here? Well, you said you don't want to see any dirty dishes in the kitchen, so this meets that requirement. But this is the same thing, okay? Because I want a mathematical expression to say that this array is sorted. If this, the highlighted portion, is what I used to describe a sorted array, then the subroutine that I have here is going to meet that requirement and say that this is how I am going to sort an array, which obviously is incorrect. If you turn this in any other classes, okay, in cisp440, okay, you're not going to get any points. So what should we do? What am I missing here?
The set of elements that are in the array A can't change.
Okay, so that's very good. Okay, so they have to change. It's just that
Well, the set doesn't change.
the set doesn't change, but the array can have duplicate elements. So now we have to find a way to handle duplicate elements. Yeah.
You have to specify that it's a valid output of the initial function that created the array.
Say that one more time.
You have to specify that it's a valid output of the initial function that created the array. Like it's within the set of the function.
Okay, we know that function is going to be important to express what we want to express. Basically saying that this is the original array, this is the final array, or this is the output, this is the input, this is the output. The output is the sorted version of the input.
Yeah, but I'm saying if you were to append to that an intersect and say like included inset of like kind of function result similar to what we had with that last function that we were testing, like not odds or evens. I forget, it was a couple class periods ago. We had a very similar like piece of logic. That would prevent that example from happening because you specify that it has to be a valid section of the function. They can't change the elements of the array arbitrarily.
Okay. I'm going to make use of a bijective function to do this. Okay, so how can we use a bijective function to express the result of sorting an array? So, getting back to here. So, so what I want to do is to say, this part here is a part of the input, or this is what is given to you. So what is given to you is the initial value of the array are the ki's. Okay, so a bracket 0, the first element of the array, has a value of k0. The second element of the array, a bracket 1, has a value of k1, say k subscript 1, and so on. They may or may not be unique. You may have the entire array only having one single value, where k0, k1, k2, they're all exactly the same thing. So there's no uniqueness guarantee as far as the k's are concerned. But all I'm going to say is to say, okay, initially, this is how the array elements are arranged. So that's given to us. So we want to, if the array is in fact sorted, then this is what we're going to say. There exists, I'm going to highlight the portion that I'm talking about because the whole thing is really long and can be confusing. So the first part here is basically saying, okay, there exists a function. Okay, it maps from the integers from 0 to n minus 1, which are all the valid indexes of the array, to the same thing. So the domain consists of all the valid indexes of this particular array, and same thing for the codomain. The codomain has exactly the same elements. Is that okay? Well, this is one of the few requirements of a bijective function, because the cardinality of the domain has to be the same as the cardinality of the codomain for anything that is bijective. Okay? And f is going to be bijective. Okay, so there exists a function that is bijective. This is the range, this is the domain, this is the codomain. And what about the rest of it? Okay, so this is the rest of it. So let's take a look at one part first. I'm breaking this up into multiple parts to explain. What is this part saying? This part is saying, when the sorting algorithm is done, then for all I, each I is basically a valid index, but it doesn't take on the entire range of valid indexes. It just takes on from 0 to n minus 2, not n minus 1, because all I want to do is to make sure that the ordering is correct. I'm just making sure that when the algorithm is done, each element in the array is less than or equal to the one to its right-hand side. Okay, which is kind of saying the same thing as what we said in the first place. Oh, what about the algorithm that initializes the entire array to 0 then? But we have a second requirement now. So now we have a second requirement, okay? And the second requirement is saying something like this. Question? Okay. So the second requirement is saying for all I, that is for each I that is in the set of 0 to n minus 1, so this time I is going through the entire range of valid indexes of the entire array, the following has to be true. Okay, so what has to be true in this case? A bracket I has to equal to k subscript f of I. In other words, the way I use the function is not on the value of the elements. I'm using it on the index of the values of the elements. Okay. Yeah.
So why couldn't it be ki? Why is it kfi?
You can change it. You can, if you want to, you can put f of I here and then I over here because it's a bijective function. So you can switch the order. But basically, what this is saying, okay, the graphical way to look at this is probably making more sense. And I'm going to try this thing out because I just got it. give it a try. It's supposedly, in this form, it can look at a letter size thing and fill up the entire screen. So I haven't really tried it yet because I just got it today. I'm going to look at VLC. I need to get the orientation right. So there we go. So it's a little bit too. Oops! Oh, the audio is going to be bad today because I just moved the mic around. There will be some really bad, scratchy sound. There we go. And we'll focus it one more time. Oh, that's the bad thing is because it's now taller. If I move the desk just a little bit, it will just kind of shake and vibrate a little more. So I just have to be careful. All right, so let's give this a try. Okay, remember all the K's. So we got K0, K1, K2, K3, all the way up to K subscript n minus 1. So all of these are values of the array before sorting, where K0 was the value of A bracket 0, K1 was the value of A bracket 1, and so on. Yep. Okay. And then we got this sorted array, A bracket 0, A bracket 1, A bracket 2, all the way up to A bracket n minus 1. Okay. Those are the finished. These are the values of the array after we are done with sorting. The function is mapping these things so that it's one-to-one mapping. In other words, it's basically making sure that each one of the K can only be mapped to one of the elements of the sorted array. One and only one, to be exact. So this way, we are double checking and making sure that things can only be mapped once, to make sure that we are not missing anything. Everything that was in the original array still has to be in the final array. Is that making any sense? So that's, yeah, go ahead.
There's a condition because for all i's elements of division n minus 2.
Yep.
I said n minus 2.
That is for making sure that the ordering is correct, because there are only n minus 1 comparisons that we have, n minus 1 comparisons that we have to do. Because the other one, okay, let me show the class here which restriction we are talking about. You are talking about this part, right?
Yeah.
Okay. So this part is only going from 0 to n minus 1 because the comparison is involving a bracket I and a bracket I plus 1. So if the range is going from 0 to n minus 1, then the one to the right-hand side of the comparison is going to be a bracket n itself, which is outside of the range of the indexes for that particular array. So for this one, it has to be one less than we have to either chop the head or the end, depending on how you tweak the indexes in the comparison. Is that okay?
Yes.
But that's a good point, because switching back to the document camera, the first requirement is double checking and making sure that we have this relationship going on between every element in the array. So together, these two requirements will basically state the correct result of a sorting algorithm. Why is it important to be able to state the result of a sorting algorithm in a mathematical way that is correct? Why is it important? I mean, you guys know what sorting is, way before you took this class, right? When you took CISD, is it 430, then you guys studied sorting algorithms? Or even before that, 360? That's way before we even know quantifiers, right? So why do you think this is important? Suddenly it has not just become important in this class. Why is it important now? Well, let's take a step back, okay? Why is it important to be able to express the correct output of a program in a mathematical way? Sorry?
To prove that it works.
To prove that it works. Okay, very good. Okay, there were some other hands. Yep.
I was able to express the purpose of it to someone else.
You can express the exact purpose of the algorithm to someone else without disclosing the algorithm itself, because this is just saying the result, but you can end up with different implementations. Bubble sort can do this, just kind of slow, okay, but it's correct, okay. Quick sort is quick and is correct. Merge sort is quick and kind of convoluted in some way, but it is correct. This is about whether the algorithm is correct or not. Does it do what it is supposed to get done? Okay? What if this is not mathematical? What if we just kind of use some loose terms to define it? It's like, oh, everybody know what it means to be sorted, so we'll just use the word, okay, just make sure the result of these of this particular array is sorted. What is the problem with that approach?
Yeah, like an array of a million elements. Like a really big array.
Okay, the big array, but the concept of sorting would still be the same regardless of the size of the array.
But I couldn't just like look at an array of a million elements and say that's
True.
sorted.
Yeah, go ahead.
You just say sorted, or specify how it's sorted, while the algorithm says exactly how it's sorted.
Exactly. Okay, so that's definitely one of those things. What do we want to apply this to? I mean, where do you think I'm heading to, taking this argument to? Because apparently, being able to define the correct behavior or the correct output, I don't even care how it is done. Okay, if you have a sorting algorithm that makes use of magic, if you can prove that it is correct, it is still good. Okay, that's basically what it is. Where do you think this is going to? What if I tell you that there's a branch of computer science and mathematics where people focus on automated verification of programs? What would be the purpose of that branch of mathematics or computer science? Why do people want to do that? Yep.
You can tell if code works before you actually test every possible input.
Before, you don't have to test it.
Yeah.
Okay, so that's the beauty of it. Okay, so I do want to spend a little bit of time to talk about this because I think a lot of times people do not understand why it is important. Okay, formal verification. Okay, so there are different names for that thing. So formal verification is one of them. And I'm going to zoom in so we can all read a little bit. So formal verification in the context of hardware and particularly software systems, software engineering to be exact. Formal verification is the act of proving or disproving the correctness of the intended algorithm underlying a system with respect to a certain formal specification or property using formal methods of mathematics. There's a lot of formal in it, okay? So just kind of skip over the formal stuff, okay? What is it trying to do? You start off with a specification, okay? The specification is going to be in the form of, what did we see earlier? A mathematical expression, right? Okay, so that's the specification. So you now have two pieces of things. Okay, so you have the actual code. Okay, I'm gonna switch back to my document camera so that we can get it recorded. Okay, so I have I did a little tape on the table so I can remember where to put stuff. Okay, there we go. Okay, so on one hand, you have the mathematical symbol thing. Okay, for all x in blah blah blah, this blah 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 has to be true. So that's a formal specification of the correct output of a program. Basically saying, okay, if this is true when the program is done, your program just passed the test. Okay. So this is what the program is supposed to do. The second piece is the code itself, the program itself, the algorithm itself. So this is basically your algorithm written in a particular programming language. Okay. There we go. So we have the code, we have the mathematical specification of what the program is supposed to do. What we want to be able to do is to have a computer program, so it's automated, that will take one, which is the specification, take two, which is the actual program itself, and come up with an answer. Either yes or no, true or false. If the answer is yes, it means the code is going to do what it is supposed to do, and we're done. If the answer is no, that means that code is not doing what it is supposed to do, and there's some problem, do not use it. Is that okay? Now, if the answer comes out to be yes, you don't have to test it anymore. Software testing is done only because we cannot do this just yet. Okay? What I want you to do is kind of imagine, what software coding really is. When you're testing something, let's say you wrote a program, for one of the homework assignments for one of your classes. Okay, let's say cisp440. Okay, so you wrote a program. You think that your program is going to do everything that you were asked to do. Okay, so let's just say that this area is the entire test space. This is basically everything that can be thrown at your program. Depending on your homework assignment, this space can be huge. So you cannot possibly throw, all the dots, throw a dart at every single, possible point of this entire area to make sure that your program is acting correctly for all possible inputs. Is that okay? So what do? You throw darts at it. So you throw a few darts at it and see if it lands on the spot, whether it is correct or not. So let's just use, I got 3 colors. So let's say the green dots are the ones where there's problem, but you cannot see it. It's behind, behind this. So the green dots are the ones that are having problems. But since you cannot really see the green dots, you're just throwing random darts, right? So you throw a dart, you pull it out and go like, is that green? Nope. You throw another dart, you pull it out and you ask, is it green? You throw one more dart, you pull it out and you ask, is it green? And after throwing, let's say 200 darts, okay, you conclude that, hey, my program is good. Well, it just so happens that none of your 200 darts land on a green dot, land on a green spot. And that's why you think the program is working just fine. But your professor, being tricky, knows exactly where those green dots are for most programs, for most common mistakes. So your professor is going to test all of these green dots to see whether your program works in all those tricky cases or not. Are we doing okay so far with this analogy? But how does that relate to what we are talking about? If your description is correct and your program representation is correct and this particular automated system is correct, if the answer comes out as an S, as a yes, that means there are no green dots. There's no need to throw dots anymore. You just turn in the program, you're done. Yep.
But how then your mathematical equation test your, I guess, how does it work together?
Aha. Okay, I can see your question. Okay, so let me tear this page out because I'm gonna have to come back to this one. All right, so we'll go ahead and do it this way because I'm gonna put it like right below this. Okay, so you have your formal description, your formal specification, which is this part here. Okay, because that's your goal. Okay, this is what you're supposed to do. So you have to keep that in mind all the time when you're writing your program. So what the automated program is going to do is to take your code here, and then it will step by step derive the actual conclusion or derive a description that describes the output, the property of the output of the algorithm itself. So we just do it step by step and say, okay, when this algorithm is done, this is the output and this equation here, okay, for all x, blah, 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 blah. This is how the output relates to the input. So now you have the expected behavior, you have the actual behavior as a mathematical expression. If this does not imply that, then we have a problem.
So you don't test all the cases, but you just...
You do not test a single case. You mathematically prove that your program will work for all possible cases.
What you say, it seems like you run your program and then you output the general equation that's the program.
I'll give you one example. Okay, so I know this is a slight digression, but I think the importance of the subject, kind of warrants a little bit more time. So I'll give you one example. Finding the maximum of two variables. Okay, which is really easy. So you say if x is less than y. I'm not using C here, just using some pseudocode. Z gets the value of y, else z gets the value of x, and if. Okay, so my claim, is, or the specification is calling for, z equals to the maximum of x and y. That's the specification. So now the question is my code actually getting that done? Well, it looks like it's going to get it done, right? So in one approach, you can throw some dots at it, right? You can say, oh, what if x is 2 and y is 6? Test it out. Okay, z comes out as 6, seems to be okay. What if x is -2, y is 20? Okay, z comes out as 20, seems to be right, and so on. But what makes you think that the next test case will not fail? There's nothing that tells you that the next test case will not fail. So instead of doing that, we can now analyze the program instead and say, can we mathematically prove that is the case? Well, let's see whether we can test it or not. Okay. So how do we prove that this program is correct? Okay. So the best way one way to do it is not to look at the code in a text form because that's kind of a little hard to deal with. So I will look at this program in a kind of more of a graphical form. So x is less than y is a question that I ask at this point. If the answer is true, I go on to this side. If the answer is false, I go on to this side. Okay. What do I do on this side? On the true, z gets the value of y. On the side of the false, z gets the value of x. And then these two branches have to merge before we get out to the output of the entire algorithm. Okay? All right. So how do we know that z is guaranteed to be the maximum of the two? So you say, well, we have a value for z. Where is it getting it? Okay. So you start at the bottom. You start at the end, You have the conclusion. Well, there are two ways to look at this too. You can always go from the beginning. So we can go from the beginning. So let's say you're here, okay? So you're here, and you analyze and go like, okay, what if we go to this branch? What is automatically known if you go to this branch? What is the condition that you know here? X is less than y. Very good. Okay, so when you're here, you know x is less than y, and z gets the value of y. Okay, so by the time you get to here, what do we know? We know that x is still less than y, right? And on top of that, what do we know about z? How does z relate to x?
X is less than Z.
Okay. X is less than z, z equals y. Okay, so we know these two facts for sure. Okay, so we'll just stay with that one. What about the other side? What do we know at this point? X is not less than y. Okay, so we can say this is just saying that y is less than or equal to x. Is that okay? Okay. So by the time we get here, we know that y is less than or equal to x, because each branch of this conditional statement does not do anything to change x or y. So the relationship between x or y does not change. Okay. But we are on top of this, we are also saying that because of the assignment statement, we also know that z is x also. Is that making any sense? All right, so if we know the condition of this branch and the condition of this branch, after they merge, what can we say? Now remember, after they merge, you have no idea which way you came from. Okay? You could have come from the left branch. You could have come from the right branch. So given that is, what you know, what expression can express, okay, but this has to be true.
A disjunction of both of the
A
branches.
disjunction, very good. Okay, so you have a disjunction. So on one side you say x is less than y and z equals y. This is z equals y. And then you say or y is less than or equal to x and z equals to x. Okay, so now you have this condition as the conclusion of what is going to happen after this algorithm executes, and you have to compare this to z equals to the maximum of x and y. Are they the same thing? So that's the question you have to ask. Okay, so we'll go ahead and do this too. What does it mean when we say z equals to the maximum of x and y? I'm going to put this away for now. We'll put it back in when it's time to do it. So what does that mean? If you have to explain to somebody, what is the concept of taking the maximum of two values, how would you describe it?
Z becomes either x or y depending on which one's bigger.
Aha, very good. Okay, but how do you do it as a mathematical expression? Okay, we'll give it some try first. Okay, so we'll give it like an intuitive try. So we'll say if x is in fact the maximum of x and y, then x is going to be greater than or equal to x, and z is going to be greater than or equal to y. Right? But there's one problem with this approach. If I only have to meet this requirement, then I can just say, well, let's just make z the largest possible integer value. Because that's automatically greater than x and also greater than or equal to y. But that's not the maximum. I'm missing something here. What am I missing? You said it already, but verbally. How do we express it in this expression?
Equal to?
Okay, it has to equal to something. And, okay, what? Okay, z equals to x or z equals y. That is how we can define the maximum of two variables or two values. So now we look at this, and then we go back to what we had earlier. This is why I like the document camera, because I can kind of move things around and just physically arrange that. So now the question is this equivalent to this? They don't look the same, but are they the same? I'm not going to spend too much time today to show that they are actually the same, but by using Boolean algebra, okay, and what you know about comparisons, you can actually prove that these two expressions are the same. You can derive one from the other. Is that okay? So that concludes that my algorithm is correct. I don't have to test it with a single test case anymore, because I have just proven that it will work for all possible inputs. Is that okay? All right. How does this relate to the Heartbleed network security problem? Do you guys still remember the Heartbleed thing? Yep, go ahead.
Their theory was correct, but their implementation was wrong because they allowed too much. They didn't have bounding on it, right? Or
Well, first of all, they probably did not even have a specification of what is proper for the program to do. What is the proper response of that program?
So they wouldn't even know if they have the correct implementation.
Correct. And that's a problem that happens a lot when people use string copy instead of string and copy, or something along that line, because they're not observing the boundary of what they're copying, or the boundary of what the content that is supposed to be of a certain length. They make the assumption that it is going to be of that length, but it really is not. Well, what I really want to say is, if every program, especially networking programs that has to do with networking protocols and whatnot, if every single piece of code is written in a way where they specifically state the specification of that code in a mathematical way, and somehow have either the computer to automatically do it or somebody to go through the code and actually do it by hand, to prove that code guarantees the specification, then we won't have a lot of problems that we are having today. Yep.
What about things like hardware issues, like operating system issues?
Same thing. The operating system is just one gigantic piece of software.
Okay, but but there are instances where we have errors with code that's purely a hardware issue, though. How would we mathematically kind of verify that?
It can also be applied to hardware, because the formal verification also applies to hardware systems. It's just that with hardware systems, things can happen simultaneously instead of kind of more in software system. We're kind of more used to things that are sequential.
Okay.
You can still prove it. We can still prove the correctness of hardware. Okay. I think that's Go ahead.
Wouldn't you need to prove both hardware and software?
Yep. Well, a lot of times we kind of assume that hardware is correct, but it's not always the case. Just gonna do one more search here. There we go. Yeah, this is something that I actually clicked on last semester. Okay, I just want to focus on this part here. a software system that couldn't be commandeered. Key parts of Little Bird's computer system were unhackable with existing technology, its code as trustworthy as a mathematical proof. So there you have it. So I'm not going to read this entire article. For those of you who are interested in computer security and how it relates to what this class talks about, you can go ahead and read this article and just use the keywords. Okay, use the keywords computer security, hacking, and use those words in conjunction with formal verification. Okay, and you can dig up articles that basically shows the importance of this particular branch of computer science / mathematics. At one point in time, I would say in the 60s-ish, 70s, people were very excited about formal verification because somebody just came up with the idea of, hey, what if we can have computers to prove what if we can have computers to derive the mathematical expression of what a particular program does, so that we can prove whether a program meets the specification or not. So somebody got really excited. And then over the next, I would give it maybe 10, 15 years of time, people got discouraged because at that time they did not have the computation power to actually do it. Okay? So the whole field just kind of died down, went into kind of like a zombie state. But these days it became, somebody brought it back because of what? Because of all the hacking, because of all the computer security problems that we have, and it's mostly because of programs not meeting the specification. So it got brought back these days, and then people realized that we now have a lot more processing power than we had in the 70s. How much more processing power are we talking about? How many years have passed? So we'll just take a quick, do a quick calculation. And yes, I am going through one of those digressions that I do in my classes. But I think this is a worthwhile digression. I think it is kind of important, especially for those of you who are still kind of deciding, okay, I don't know what I want to do in my future, what I want to study, what I want to specialize in the future. So let's say we're talking about 1975, and now it is 2017. How many years have passed? 42, okay, so 42 years. In 42 years, how many 18-month periods does it have, or 1 year and a half? So just divide 42 by 1.5. 28, okay. So we have 28 18-month periods. Why do you think 18 months is so important? Because of Moore's law, right? Moore's law says what? Every year, every 18 months, the density of semiconductor stuff will double. Okay, and approximately it is kind of related to the speed and performance of hardware as well. Okay, so we kind of do a rough estimate, of performance using the same scale. So we are talking about, this is the factor. 2 to the power of 28 is the factor of a computer in 1975 versus a computer today, using the same amount of money to make it. Okay, how much is your cell phone? I bought a cell phone for my daughter, brand new from Amazon, $150. It is an octa-core cell phone. I don't know how they can make it. I have no idea. $150 today is worth how many dollars in 1975? I have no idea. 15, 20-ish. Okay? How much are computers back in those days? How much is a personal computer back in 1975? Do they even have personal computers in 1975? Nope, they don't. So we are talking about a vast amount of computation power today that is unheard of back in those days. So that changes how we look at automated program or formal verification, because what was considered undoable simply because there's not enough processing power back in those days is now practical again. Okay, another example. Yeah, go ahead.
Can we pass out the roll sheet?
I don't have a roll sheet today. Some people go like, okay, shouldn't have been here. Okay, so think about another thing, MD5 hash. Okay, how many people know what is MD5 hash and how it is normally applied? Okay, I know you do. Okay, so MD5 hash is something I am kind of surprised that as computer science, in the computer science class, not too many people raise their hand and go like, yeah, MD5, I know what it is. Okay. Sorry?
Is that where you take a private raise of power?
No, it's an actual algorithm, pretty simple. The algorithm itself is published, and you can find Java, C++, JavaScript implementation of the algorithm left and right. Okay, but it's a known algorithm that will take something and it will hash. It's a hashing function basically. So it will take a string as an input and hash it into a 128-bit result. It's just a hash function. So the idea was, if I use MD5 to hash a password and then store the MD5 hash of the password, then it will be okay. Even if the hashed password is to be stolen, the original password, what you actually have to type to generate that MD5 hash, cannot be reversed. So it will be okay. Okay, so I'm just giving you an example here. So let's just say PASSWD, these 6 characters maps to this particular hash. Okay. A computer system would not store this password in plain text. Instead, it will store the MD5 hash of the password itself. Is that okay? So every time you want to sign into the system, what you would do is on the terminal, you would type in PASSWD. When you press the enter key, the computer will look at what you type, computes the MD5 hash of that. Okay, so it will compute the MD5 hash of what you just typed, and then try to match that with what is stored in the system. If the hash value stored matches the hash value of what you typed, then it will say, okay, you're good. Okay, you're allowed to get into the system. Okay, if this MD5 hash is to be stolen, you can type the MD5 hash here in place of the password. The hash of the hash itself is probably not itself. Okay, I'm not sure whether there is a case where the hash of an MD5 hash is itself. Okay, probably not the case. Does anyone know for sure? Nobody? Okay.
It uses prime numbers in creating the
So it cannot have a hash being its own hash? Okay. So that means if you type in a hash, you can never match the actual stored hash. Okay? So that was considered really safe, okay, and that's why they put a password file at a place that some people can actually get to. Well, it was safe during the early days of Unix, okay, to be exactly, it was Unix. So that would be in the late 70s, the 80s, and so on. But by today's standard, it is not safe anymore, because somebody created a rainbow table. Okay, so what is a rainbow table? There we go. So a rainbow table is a pre-computed table for reversing cryptographic hash functions, including the MD5 hash, usually for cracking password hashes, which basically means if somebody knows the hash value of a password, they can type that hashed value into a table lookup website, and they can find a string, not necessarily the original one, but they can find a string that can generate exactly the same hash. Okay, so that's why when people steal MD5, not MD5, when they crack into a MySQL database or some other databases, and they retrieve the MD5 hashed passwords, then you can reverse it. You can actually get logged in, as those people at that point. And that's how, I'm not sure whether that's how, the Yahoo accounts got hacked and other, well-known, email services got hacked, but I'm suspecting that might have something to do with it. Because a dictionary attack can succeed in some accounts, but not universally. And I think there are instances where the accounts were universally hacked. In other words, it doesn't matter how difficult you make your own password, it is still hacked. And this may be the reason behind that. Okay, what is the point of all of this? I know I'm digressing, but what is the point of this part?
Cybersecurity is more important now than ever.
Say that one more time?
That cybersecurity is more important now than ever.
Okay, that's one. Okay, very good. But why is it more important now than ever? Yep.
Because hackers have more resources now. Like it's easier for them to get into things that previously weren't easy to get into.
But why is that? What makes MD5 hash used to be secure and not secure anymore?
Because the computational power needed to backtrack one in the past would take it longer than your natural life.
Yep.
And now it's minutes.
Exactly. That is exactly the case. So what we are studying in this class about correctness is actually important as well, because formal verification was deemed to be a unrealistic goal, okay, back in the 80s. So that's why everybody gave up, in that time to basically say, okay, with this kind of computation power that we have, there's no way we can actually do anything useful with it in terms of formal verification. But now we have a lot more computation power than we had before. Now there's no need to do formal verification on everything. For instance, Microsoft Word, I don't care. Okay? But what about your Linux kernel? Maybe that's kind of important, okay? What about your SSH server and client? That might be important, okay? What about the SSL libraries? That might be important. So you can focus on the key portions of a system where computer security is of major concern, and apply formal verification resources to those really key points first. Okay? Because your front end can crash, okay, but if you're not going to lose any data, okay, that's okay, not a big problem. Your browser can crash. It doesn't, if it's just crashing and it's not leaking data, it's not a big problem. Okay, so that's why I think it is kind of important to understand the reason why. So now I can bring the whole class back to where we started in the first place. Okay, so that's why this is important. Okay, because just by telling someone that, oh, I want this algorithm to sort an array, and I think you know what sorting is, that's not good enough as a specification. Okay, because that does not allow a formal verification system to kind of chew on the code and come up with that conclusion and say, yes, it does sort, or no, it does not sort. Is that okay? All right, so we are running out of time. I'm going to end today's class 2 minutes early, so we'll make it up later. You guys have a nice weekend, unless you're in my CISP 310 as well. And if you want to go take a 10-minute break and come back in about 10 minutes.